So my name is Riley. I'm going to say real time probably a million times in this thing. I want you to know that that's a habit. I don't actually mean real time in the sense of real time systems. I mean online or continuous processing. When I say real time, I'm going to say real time probably. It's just a habit. I'm sorry. We even call the name of my team de-duped, which means Data Engineering Real Time Platform, which isn't really real time, but whatever. So that's me. I work at AppNexus. For those of you who don't know what AppNexus is, it is a advertising technology stack as a service. So we do an exchange. We are an advertising exchange, and I'll go through what that means for those of you who aren't really sure how advertising works on the internet, at least programmatic. It was founded in 2007 as a cloud hosting company. The idea was to provide cloud hosting services a la Amazon specifically for ad tech. And when that ended up being extremely capital intensive and hard, they sort of switched gears after a year and got into the exchange business, which is the vast majority of what we do today. We see about 30% of the internet display traffic, and the guess is that we actually see this more than once. I'm actually not going to talk about that, but if you're curious about why that happens, I'm happy to follow up with you afterwards. To give you an idea of the scale we're talking about here, I don't know how those numbers didn't come out very well, but our all-time peak queries per second into our internet-facing machines, which we call the impression bus, hit 5 million queries per second in January of this year. So generally, the fourth quarter for advertising and rolling over into the following year for programmatic is very, very expensive, very, very busy time of year, because most budgets are spent around Christmas for advertising, and when all those contracts expire at the end of December, January becomes almost all programmatic because there are no pre-deals sold yet for the year. So they sort of all fall over to programmatic. So we see a massive amount of traffic in January. So in January, this is zoomed out. This actually says 3.5, and it's averaged out because it's a very long view of the whole year. But this is the actual day. We did, just for a second, touch 5 million queries per second. So it's a lot of things fly in at us. Basically, almost every web page you visit probably hits us in some way or another, whether it's a pixel or an ad or something. So we see, as you can imagine, a lot of data. More traffic stats. So 5 million all-time peak. Our current low is about 2 million on a daily basis. So we have a very seasonal or daily follow the sun sort of pattern to our traffic. The current peak's around 4 million. Our all-time peak of actual auctions. So not all of these queries are actual auctions for ad space, which I will get into the mechanics of in a little bit. Some of them are just pixel fires or clicks that come in or other kind of data callbacks. And in total, we do around, and this is true today too, we still do around 120 billion auctions every day. So this is what our platform looks like. It's kind of hard to see up here, I'm sorry. So we have two forms of traffic that come in, two main forms of traffic. We have tag on page traffic, which would be a slot for an ad somewhere, like a banner ad at the top of your page, right? And then we have SSPs. SSP is an industry term for someone else who is an AppNexus. It means supply side platform. So they have some stuff that they want to sell. The impression bus will talk to various third-party bidders, right, who plug into the AppNexus platform to bid on traffic. And then we also host this service for people who aren't technologically capable of writing their own bidder. And it actually turns out it's really, really hard to write a bidder for traffic you see on the internet. And I'll talk about that more in a second. So I'm going to talk mostly in this talk today about the bottom half, or the bottom part of this graph down here, about PackRat, RatSoda, Kafka, and the data pipeline, and how we process all this stuff. I'm just giving you an overview. So we do all of these real-time transactions, all these auctions, 120 billion auctions a day. We do them in 120 milliseconds per. And this is a sort of self-imposed speed limit because it's a user experience issue. Anything that starts to get longer than that starts to really drag down the page and make it annoying to use. So we have hard cutoffs where we will blank or default or send up a PSA after 120 milliseconds goes by if we don't get a bid back or everybody times out, right? So we structure our real-time apps this way. Paul, if you saw Paul Kwong's talk yesterday, he covered this a little bit. We actually don't share code. We don't share state, across multiple threads. We run multi-threaded apps, but they're all independent operation with a sort of a shared object cache, right? So we'll have a control thread, right, where we're able to communicate, get metrics out, and talk to these various machines, of which there are thousands. And that's the write portion of our SPMC workload. So we'll write data into the control thread, which is responsible for writing into shared data structures for the application. And then we'll have these bunch of worker threads that are wholly reside. They just read off of the object cache, and then they apply the logic of the auction. We do everything largely lock-free. We do use SSTM, our own implementation that Paul wrote of software transactional memory, to save us from locking in a lot of spaces. We write in C. The whole stack is C from bottom to top. That's basically a bad decision, but it was taken before we got there. Yeah, so that's what the apps look like. So this is really hard to do. Sorry, it's not advancing on your screen, but it advanced on mine. There we go. So this is a graph of third-party bidders on our platform and their timeout percentage. So they have 120 milliseconds to respond to a bid request. And people that try to write bidders for our platform, you can see we have somebody at the top there who times out almost 95% of the time, constantly, all day, every day. They just basically don't bid on anything and just take up cycles. I don't know what they're doing. It's horrible. I've kept all the names off of this. I don't want to embarrass anybody. But you can see even the better ones have this, as the load on the platform spikes, they get these massive amounts of timeouts. And we have varying quality throughout the platform. Now, I'm going to show you the next slide, which is our timeout rate. You can't see, if you look closely on the bottom there's a little tiny blue line, and once in a while it hits 1%. Now we do have the advantage of it is our platform. We are nearby. We have lots of machines. I think there are 1,500 bidders worldwide that handle this traffic. But it's a hard problem. It's a hard sort of ecosystem to work in. So that's sort of all primer. So the advertising exchange. This is the simple case. When there's a tag on the page, one, there's a web request for an ad that comes into what is our impression bus, right? And in two, the impression bus will construct a bid request, which I'm leaving out some stuff, I'm simplifying here, but the impression bus will take information about the site and the user and some other stuff we've looked up, which I've left out of this slide, compose it into a bid request, which is information about this ad slot, size, site, yada, 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 and send it on to bidders, including our bidder. So that gets sent on. The bidder has 120 milliseconds to respond. Our bidder responds in about 5 milliseconds. That's the response that comes back in 3. After the response comes back, the bidder then collates all these responses from all the bidders, ranks them, picks a winner. After it picks a winner, it actually logs out the impression. So at this point, we say, OK, we know who won. We're happy. We have our information about our transaction, and they log it out to something called PackRat, which I'm going to talk about in detail in a little bit. They will also send and notify, it's another web request, back to the bidder to tell it that it won, right? So it can keep track of its budget and do other stuff. And then the bidder itself will log out a different piece of information. So on the impression bus side, we have all of the sell-side information about the site, the transaction, et cetera. The bidder will log out buy-side information about the creative and the campaign and all that other stuff, right? And these things get thrown together in PackRat, who then forwards them on for data processing, which I will get to in a bit. Now, that's the simple case where we own the traffic. Where we don't own the traffic, when we are third party to another exchange, like Facebook Exchange or AdX, right? We have a wholly different not wholly different, but different way that we have to process this data. We get a request from an SSP like Facebook, right? We do the same thing. 1, 2, 3, 4 are all the same, right? We make the bid, we get the response, we rank them, we pick a winner, and then we tell Packrat there was this impression, and we tell it. But then we can't actually log out the buy-side information because we don't know if we won. We don't know if we won the auction because it's somebody else's decision. It's Facebook's decision or AdX's decision, right? So we send our best bid back to the other exchange, and we wait, and we wait, and we wait. And sometimes we wait for a long time. At some point, they will send back maybe a win notification, which says, hey, I picked your ad, you won, right? And so then the impost will log out a different piece of, well, first it'll notify the bidder, hey, we won. And the bidder will log out buy-side information, right? And then the impression bus will turn around and log out sell-side information, extra sell-side information, because something may have changed in the time when we logged out the impression, and then we contact the other exchange, and it came back. The type of impression may have slightly changed. Who the seller is may have slightly changed. Who knows? And then it comes back through as a different thing. So now Packrat has 3 artifacts that come in: the impression, the bid, and this new thing, which is an accept, right? So what is Packrat? So Packrat is this homegrown data router that we use at AppNexus that takes data in, recombines it with other data from other machines, and forwards it on to other Packrats, where it eventually is put on disk. It's basically buffer compress and forward. We work in an ecosystem where a certain amount of loss is expected, right? It's not unusual in the advertising industry to have a 10% discrepancy rate between our ad server's set of records about how many impressions were shown and seen and somebody else's ad server's set of records, because there's so many things flying around, it's hard to keep track of them all, right? So we live with a little bit of loss. But we have to do this in order to get throughput on a reasonable number of machines. So it's basically high volume, parsing these rows, writing them to disk in append-only logs. We do parse and validate every row, and we give at least once delivery by default unless we crash. So that means if a post, this is all HTTP, if a post to another Packrat fails, we actually log the information to disk. We have another program that comes along and picks it up and keeps retrying until that succeeds. We live with duplicates in the platform for that reason, but we do have exposure to data loss in a crash situation. So this is what, there it is, sorry. So this is what it looks like. AMS has to send data to New York 2. That post fails for whatever reason. There could be a network partition or a timeout or who knows. Someone restarted the Packrat in New York at that particular moment. So then we go to disk. We have this other program called repackd, which picks it up from disk and forwards it on. Really simple. And then it succeeds eventually. Another idea of the scale, we do this about 1.5 billion rows a minute come through Packrat. It's a lot of data. I don't know if anybody has a similar scale, but it's a crazy amount of impression and bid and stuff just flying through this. We do compress this down as we send it over the wire with Snappy, so we get some savings there. We also combine, obviously, requests and send buffers at a time. So we get this down to about 3 million actual HTTP requests a minute to send this data around the world at peak, around 3 million, 3.5 maybe. And in total, compressed on the wire, it's about 60 gigabytes a minute of data that's flying around this network. So it's a lot. I think you get the picture, it's a lot. Okay, so this is where Packrat is stationed throughout the world. It's in every one of our data centers. So we have, where the black arrows are, we have New York and LA, our master data centers, which I'll talk about in a second. We also have data centers in Amsterdam and Frankfurt, and we have one in Singapore to serve that area of the world. So New York and LA are master data centers. So one of the things that Packrat does is the slave data centers just buffer and forward, and they don't touch the disk unless there's a failure. But in New York and LA, we actually log everything that comes into disk so that it can be picked up and shoveled as fast as we can into Hdfs for processing. And I'm going to talk about that too. So the Hadoop clusters, the two Hadoop clusters we have are in New York and LA. New York is the primary processing data center. LAX is a hot backup. It's running all the jobs all the time. We're just not relying on them. So we group every set of information that comes in by like type. So we have a topic in Packrat for impressions. We have a topic for bids. We have a topic for win notifications. We have a topic for clicks and pixels. We then batch these all together. So impression bus 1 sends us 3 impressions, and impression bus 2 sends us 3 impressions. We put these all together into one container, right? We prefer a min size, which is 128K of buffer in Packrat, and we fall back to a 10-second wait. So we have various speeds of frequency of data for different topics. And some of them are pretty slow. Like a click comes in very, very infrequently compared to the actual conducting of an auction, right? So the auction topic will be flushing out in milliseconds, and then the click one might wait 10 seconds to fill up to an acceptable size before it flushes. We snap and compress everything in its HTTP post. I covered that. So initially, all the Packrat communication on our platform was ASCII tab separated. And I don't know why, but it's really bad. So there are a lot of concurrency bugs, or were a lot of concurrency bugs on our platform. And ASCII tab separated is horrible. There's no schema. There's a schema in Hive, right, or in Hdfs. There's a schema for this table. But there's no way to validate this on the wire. If I interpose multiple rows and send them out as one log row because I have a concurrency bug, you actually could have valid, correct data by type in the correct spot, which is completely wrong, and there's no way to tell because of that. It's really bad for validation. It's great for compression. We still do support it because we still do have some clients who communicate ASCII TSV, so it's a sort of legacy thing we have to support. But most of our traffic is now AN message, and I will cover AN message in detail as we go. So I'm pausing for water. Any questions so far? Good. Does everybody feel like you understand advertising a little bit? All right. Now I'm going to talk about how we process this. First, the batch. So batches, impbus, and bidder send all this information through Packrat. Packrat writes to disk. We have another program called Courier, which picks up this data, right, and shovels it into Hdfs. Right now, it's protobuf. I'll talk about that in a second. And then we have these Hadoop MapReduce jobs that do these massive joins across all this data and produce a bunch of crap, which is shoveled into Vertica and shoveled into another spot in Hdfs to be available for client download. Like they want to go get their actual log level data about transactions that happen on the platform. So we have an API for them. They log in. We actually serve them a file right off of Hdfs right today. That takes about 2 hours. It takes like 110 minutes on average to produce any client's standard feed. That means, and I'll go over why that is in a minute, but it's a really long time. That means if you see an impression right now and you want to go get your log level data about it, it means 2 hours later you can finally download a report that happened 2 hours ago. So it's not a good way to react to changes. We also have this problem of, I talked about this a little bit earlier, about time delay. So win notifications can be time delayed. This means Facebook may tell us sometime in the next 12 hours that we won an auction. And this makes joins particularly interesting. They're so disjoint in time sometimes, very, very infrequently, but sometimes, that it becomes actually a difficult problem. It seems to set up nicely for MapReduce, right? You just dump it all in a bucket, all of this, something. They have we know when the auction was, right? So we can put it all in a bucket that was the time of the auction. And then go back later and process it. The problem is if something comes in 10 hours later, what do you have to do? You have to go back and reprocess that bucket, which is actually really expensive. In earlier days at AppNexus could actually cause us to fall behind if we tried to reprocess. We couldn't actually reprocess because we couldn't get the jobs to complete quickly enough while processing all the other data at the same time. That's how much data it is. And most exchanges do not do loss notifications. If they did, this would be easy, right? You'd have a full record that we won or we lost, and we can join all the things together, and they're all in the same spot, and we're done. But since we don't get loss, the joins get very, very sparse. Hold on, I'm waiting for this to catch up. Yay, Wi-Fi. Oh, there we go. So joins are very sparse. The top line here is number of impressions. The green line is the number of impressions we'll see per minute. It's about 1 million and change a second. The blue line there are the number of bid rows that we see related to those impressions. And then the red line there at the bottom are win notifications that come from third-party exchanges. So somewhere in this sea of data are transactions that are complete, right? Some of them don't require a red line, some of them do. Most of them require a blue line, sometimes they don't, and it's a kind of a messy data model. So this is how processing went at AppNexus over the years, and I actually learned this recently preparing for this talk. It's kind of a probably pretty typical way that data processing has sort of evolved over time. When they were very, very small, they've always had packrat, but when they were very, very small, they had ASCII logs and this program called Data Loader, which was like a Python script effectively, that would push everything into MySQL, and they'd run these MySQL queries, and that would produce reports, right? And then scale started to get bigger, so they went out and bought a very expensive machine called a Netezza. Has everyone ever used a Netezza? Big data processing type, purpose-built for data processing. So similar process, swap out MySQL, put in Netezza, and then that one started to get hot, and so they got another Netezza, and then they did Netezza 1, and they pushed it into Netezza 2 to do different kind of reports that way, and then that got really hot, and so then they said, okay, let's just get a whole bunch of Postgres boxes, and we'll shard our data across the Postgres boxes, and from what I understand, this was horrible because they had to, instead of sort of partitioning and sharding in an intelligent way, they would just give up and stand up a whole new set of Postgres machines and just move over to them and turn off the old ones. And so then someone intelligently figured out that Vertica existed, and we went from Netezza directly to Vertica, which solved sort of the scale. We still use Vertica today, which is great. I love Vertica. Eventually, Netezza processing got replaced with a switch to Hdfs and Hive. So initially, all of our queries were just Hive unoptimized Hive SQL. Eventually, the Netezza went away, and we figured out we can go right from Hive to Vertica. That was great. We have a sync job now. And then the last step was eliminating we still have Hive for some of the lower priority jobs, but the last step was eliminating Hive for custom handwritten MapReduce, so we can win some optimization. So this is what it looks like today. Today, we don't send ASCII into the data pipeline. We send AN message. We send protobuf, effectively, and I'll talk about what AN message is in a minute. But protobuf allows us to get many gains, both in speed, parsing speed inside the data pipeline, correctness and validation, in that we can add validations on top of protobuf when we're pulling rows in, so we can discard rows that don't pass validation. We store as protobuf or as Parquet inside Hdfs for space reasons. I'll get to that in a second. We then MapReduce Vertica reports. We also have a second thing that has cropped up in recent times, which is the Kafka Ratsoda Kafka Samza streams path, which is dope. And I'm going to talk about that in a minute, although Kafka. So AN message is sort of a homegrown data agnostic wire protocol, right? It's a really simple header that describes a message schema identifier, a format of that contained data, and then a payload, right, effectively. So we make these specifications in JSON, which outline arbitrarily complex data structures. We then generate code in C to serialize these to protobuf avro JSON, something we call native, which is effectively a wire copy, a mem copy, with some allowances for arrays and strings. And there's a reason that we do that. It's faster. Not so safe, but very fast. And this allows us to have a lot of flexibility. This allows packrat to communicate in one direction from, let's say, the impulses and the bidders as a very fast native format, right? And then translate this, transcode it, and dump it on disk as protobuf for somebody else. It's the same code base. We don't have to think about it. We just tell it, switch your format, and it gets serialized out as something else, which is nice. It allows us flexibility for what consumers want to consume data in. if we need to produce a whole bunch of JSON rows, we can do that for somebody, for debugging or for whatever. We don't prefer to do it because it's slow. So these are in ticks to process, I think it was 1,000 loops of a message. I forget. Anyway, native serialization a little bit slower than deserialization is very, very fast. Proto-serialization is slightly slower, and deserialization is slightly slower, and then JSON, of course, is off the chart slow compared to the other formats. So we tend to prefer send data on most of the platform as native because it's a lot less work to do, and we can do it with a lot fewer machines. So where COGS is king, which is the ad serving business, we gain a lot of efficiency this way. We do all of this work on 21 pack routes. That 1.6 billion rows a minute gets processed on 21 machines. So we also do Avro. I didn't include it on here because it's so bad performance-wise. At least Avro C is so bad. I don't know if Avro in another language is written better, but Avro C is just really slow. So we don't even bother to compile it in to the platform because nobody uses it. So for batch processing, we process 170 terabytes a day inside Hdfs. We have 400 ETL jobs or more. We have 250,000 analytical reports generated every day. As I had mentioned before, 2 Hadoop, 2 HBase. HBase on our platform is used for really long look-back conversion attribution. So if you see an AT&T ad at some point and click on it, and then like 10 days later, you buy an AT&T phone, right? They have a pixel that they'll fire back that says, oh, they bought a phone from that ad 10 days ago. This is a conversion. And they actually pay quite a bit of money on conversions. Some conversions are like $100. Like they will pay $100 for a conversion for someone who buys a cell phone. So they're very, very valuable, but they're very, very hard because the average look back on a conversion is 33 days. So we've got to store 170 terabytes, not all of it, but some portion of 170 terabytes for 30 days, and then go find that impression when the conversion event comes in and snatch it back and complete the transaction. So that's a very expensive job, as you can imagine. We have 6 Vertica clusters, and all of this is on 1,200 bare metal servers, including disaster recovery. So it's about, in Hadoop, as data nodes, it's about 450 in New York, about 460 in LA, and then if you add on Vertica and all the others, it adds up to around 1,200 servers. This is what HDFS storage looks like. Initially text, so the average impression file that Packrat would write out, I think it's about 1 Packrat for 5 minutes would be about 370 megabytes. Right? When we snappy compress this inside HDFS, we get it down quite small. When we switched to protobuf, we got it down even smaller, plus we gained processing efficiency in not having to parse long, 64-bit integers out of text and turn them back into integers so we could do something and then write them back as text later. It was really stupid. Now we've moved on to Parquet, which is a columnar storage format for HDFS. If those of you haven't looked into it, I suggest you do if you have a lot of data, because it's going to save you a lot of space. And it's actually faster since it's columnar store. Jumping through columns goes very, very quick. This is what the HDFS process looks like at sort of a very, very high level. I had mentioned HBase. So we have all these things that come in. We have to join them together to create the transaction of the ad thing. We then have a separate path that does click attribution, right? And then I had mentioned conversion attribution. That's the long 30-day job, right? And we take all this data and process it, and we push it into Vertica. So the HDFS process, because we don't know if data is going to arrive late, right? We have no real control over that. Some upstream network partition, some machine got shut off and there's data sitting on the disk. You turn it back on, the data gets flushed out. So data arrives late all the time. Plus, we have a little bit of buffering in the way we deliver data. So the solution to this, the practical solution to this, is just wait. So what we do in the data pipeline today is we wait for 10 minutes. So the hour flips, right? We know all the rows being generated from now on are new, and we have to just wait for the old data to trickle in. We wait that 10 minutes, and then we kick off these jobs. And the job that does the join of impressions, bids, win notifications, right? That takes 12 minutes to run. We use 2,400 maps, 1,500 reducers. There's a little bit of, it's a little bit unclear to me how you size yarn containers to bare metal. There are two ways to do this. We run on 12 core machines. If you figure you have one yarn container to every core running on the box, this job costs 325 machines for 12 minutes. If you go to the theoretical maximum that we set up our boxes at, which is 25 yarn containers per box, we run this job on 156 bare metal machines for 12 minutes, and that's all they're doing for 12 minutes. And that is a lot of machines. So now the stream stuff. So recently we had a lot of client requests and internal requests to get at this data faster. People wanted to see their log feeds like right after it happened because they wanted to be able to go do their own offline optimization of their own campaigns and see this data as it happened and dashboard against it and do all kinds of cool stuff that you can do with analytics today. So we thought, okay, we're gonna do this. So PackRat was altered to using the fairly excellent RD Kafka library. If any of you are working in C or C++, RD Kafka, pretty fantastic library for publishing and consuming very, very fast to Kafka. PackRat was augmented to pull in the RD Kafka library. It is now a producer into Kafka, right? And then we have another piece of software, which I'll talk about in a bit, called RatSoda. As you can tell, I'm great at naming things. RatSoda stands for Real-Time Structured Object Data Aggregation. And it is a complex event processor that we wrote in-house in C, which has some interesting properties. It's very, 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 very fast at what it does. The existing products, the Espers and the like, that existed for complex event processing just fall over when we send 10 million rows into it. So we needed a solution that would actually be able to scale up to our scale. And so we said, okay, well, we're going to write one. Famous last words. Then we have another sort of hanger-on of the Kafka process, which is a set of processes written in Java, which basically just pull on completed topics and push them outside to the outside world, right? So we provide feeds that go out to clients on our platform who want to see their data in real time. We'll do this calculation, and we have it's basically a simple forwarder. It just pulls off of Kafka, pushes into Kinesis, for example, or pulls off of Kafka, pushes into Rackspace, Cloud Queue, whatever it's called, right? So so this is what it looks like. So how many of you know what Kafka is? Oh, yeah. How many of you have good experiences with Kafka? Just one. Okay, 3. Okay, a couple people. So I love Kafka, and I hate it. It, unfortunately, is the best tool for the job right now. There isn't anything better that can handle sort of this volume of crap. But at the same time, it has some deficiencies, which I will get to in a bit. So quick primer for most of you know what this is. It's durable pub sub queue. Data is replicated about the cluster. The consumer maintains the offset, which is great for slow subscribers. You can get very, very high throughput. We send, for this job, into Kafka 1.2 to 1.5. I did this yesterday. I guess it was a slow day. 1.2 to 1.5 million rows a second get pushed to do this join. In total, in New York, we're pushing about 2.2-ish million rows a second into Kafka. And for the most part, it's great. It doesn't fall over. We push these all as individual protobuf messages into named topics and can pull them out. We run these, if you guys want hardware information, they're all run in the same data centers as PackRat, so they're all local to the network. We run these on large clusters, 32 nodes, right? They're all 12-core E5s. They all have 12 disk at 1 terabyte, 10K SAS rates. We don't use SSDs. We use spinning Rust. We also, interestingly, use RAID 6 instead of a RAID 10. And this was actually a mistake, but a happy accident, and is a good story. The SA that I had asked to set up these machines so we could bring up this awesome Kafka cluster accidentally made them RAID 6. I guess his kickstart script like took 12 disk machines and made them RAID 6. So he made RAID 6. I said, no, we don't want RAID 6. We want RAID 10 so that we can have better throughput. And you're nodding too. But he said, F you, dude. I tested the throughput, and RAID 6 is faster. And I said, I don't believe you. And we spent the next couple of days pounding this RAID on several of these machines. And it turns out RAID 6 is faster. For the bigger chunks of like 64K chunk writes at a time, RAID 6 was faster, so we stuck with it. Plus we get RAID 6. We run 128 gigs of RAM. We run the Kafka VMs at 8 gigabytes of heap space for the Kafka process. Now, the bad. We have hit every one of these. If these slides are up online, you can go look up these things. I'll talk about them briefly. I'll talk about one in a little bit of detail. We have run into compression issues where the SAMZA version of Snappy is slightly different, and compression had to be turned off for SAMZA producers because that's horrible. We had topic deletion issues. If you're too aggressive about removing topics, then the topic gets in this weird-ass state where nobody can delete it, and then all traffic stops on that broker for a while. We've had some weird ones. We've had the dreaded Kafka 2082, leader not local. If you guys ever run into this, if you're pushing a lot of data, there's a bunch of race conditions that still exist in the Scala code base here that don't do such a great job. It's hard. It's really hard to get this right. And they don't do yet such a great job of responding to, oh, I lost my Zookeeper connection, but I have old metadata. I'll just keep serving traffic. No, that's not mine, even though the controller now thinks you are the leader, and you don't know you're the leader because you can't talk to Zookeeper. And so all traffic for that partition topic would stop, right? Unfortunately, the only solution to these issues is to restart the cluster, or at least restart the controller and the machine that's in trouble, right? Or patch. There are patches for some of these, if not all of them. We could patch Kafka and run a non-release version, but we don't, as a company, have a really giant pool of Scala expertise, number one. Number two, I don't really want to have my own fork of Kafka that we run just so that we can get the work done. I would like to just run the product that works because I don't want to be an expert in message queuing. So this is an illustration of 2082. So you have the brokers are in blue and the Zookeepers are in purple. And what happens is the broker loses a connection with Zookeeper, but it keeps a copy of metadata that it last knew about. And then, I didn't illustrate this on here, but then the leader switches, or the controller switches, right? And a new leader is chosen for those topics because it's down, right? Because it can't talk to Zookeeper, which makes sense. It goes down. The broker is not available for those topics. So it goes down, but it's not down. And then since the metadata hasn't updated, any client connected to that particular broker who doesn't know that all the metadata about the topics have changed is still telling them the wrong crap about where to send data. So they're still sending it as if it's the leader data that are meant for it, right? And we get all of these leader not local because some metadata updated in some clients and not in others because depending on which broker they're connected to. And it ends up being sad. And this is what happens to Packrat. So we start seeing all this back pressure, right? Packrat can't serve anything. And this is, since it's so much data, the catch up from the backlog that happens as a result of this is actually quite significant. Right? It's almost like you have to plan capacity for these disasters just so that you can catch up when the next disaster happens, when it's going to happen in the next week or something. And you have to plan all this extra capacity, which you wouldn't normally need, just so you can consume all of the crap that gets flooded in once it gets fixed. Right? So I would say on Kafka, just in general, it's great. I think if you are in an environment where loss is okay, where it's okay if the cluster goes down for a little while and you can just drop the data that you would have sent into it on the floor and you don't want to have to plan extra capacity to deal with it, then absolutely use it, right? If you have sort of a very high throughput system like this, you're going to run into this stuff. So just be aware if you're going down the Kafka road that this is probably going to happen to you. Now, if one of you fix it, you'll be my hero forever and push it back upstream. Or if one of you writes a better one, you'll be an even bigger hero. So, Ratsoda, how am I doing? Oh God, I'm almost out of time. I gotta speed up. So, Ratsoda is a homegrown complex event processor where we do high volume aggregation, deduplication, joins, maxes, top N, things like that. It's a Kafka consumer and producer at this point. So we used to push directly from Packrat into Ratsoda, but then we had this sort of durable queue in the middle, so we use that so that we can have some history and backup if we mess up. It operates on windows of time. You can think of it like a mini MapReduce or real-time MapReduce, sort of like Spark streaming works. Operates on windows of time, and we invented a language to control the operation of this thing, which we should have taken like a Lua or a something and made that the language of control for the scripting of this. But at the time, we were trying to get something out the door quickly. So we invented this very, very simple stack-based reverse Polish notation language. So we could write scripts to make this thing operate. All the scripts are single-threaded by design. You saturate a machine by running multiple scripts, one per core. It's capable of processing millions of rows per second per node on like an 8 to 12 core machine, which is great. We are porting our DSL to JavaScript as we speak. For this particular thing, I'm going to talk about the join section of Ratsoda. We actually do joins on disk in Ratsoda, where data comes in, it goes to disk as an append-only log, so individual protobuf rows get written to disk. We also use LMDB, which is a great library for those of you working in C who need an embedded KV store. LMDB is fantastic. We use LMDB for a transactional snapshot of what rows have arrived and when the join is complete for an individual thing. We can exploit time. So we wrote custom software to do this join because it's so expensive. But the idea that we can exploit is that most of the joins or most of the information that's happening, since it's all happening in real time, is all happening close to right now. And because it's happening all close to right now, most of the files that we're accessing are already already in file system cache. So we can operate on the file system as if we're operating on RAM. So it goes really fast, which is great. Recovery is instant, so we pull out a Kafka and write it to a local RAID 10 in this particular case. The offsets are managed locally as well. So if we take a node down, bring it back up, it just goes back to the spot it was and keeps pulling data down and putting it on disk and continuing with its joins. We can do 700,000 sparse joins per second per node in our system, which is about 1.5K per join. So it's about a gigabyte per second sparse join speed. It's very fast to do this stuff. We basically push the disk as fast as it can go, which is great. So the bad part is we have this is how you control it. This is what the DSL looks like for Ratsoda. It's a little ugly. We're correcting this problem as we speak, actually. Don't do that. Do this. So Node.js is this great product for server-side JavaScript. And we thought, why not JavaScript as a data processing language, right? So we're actually translating a lot of the stuff and the power that Ratsoda does into JavaScript. So you can write JavaScript and do all of this Kafka connection, all this queuing and deduping and all the stuff you would want to do for complex event processing, and then spit out an answer as another topic into Kafka. Do all kinds of cool transformations and aggregations and joins and spit it back up. It's very cool. So going forward, hopefully soon, we will start moving our custom DSL-based scripts over to JavaScript and actually running that in production. We're not quite ready yet. So this is what the glorious streaming future looks like. That's the batch on the left. We now have the streaming on the right. It's great. This is the statistics. We have a max 10-second latency on 99% of joins that happen in production when we stream them. We do 6 hours of look back instead of 1, which is what the batch system does. And we do this on 10 bare metal machines. For comparison purposes, batch, 12 minutes. It's really, really high latency. We use hundreds of machines, depending on how you measure it. On the stream size, we do it on 10 machines. If you count the Kafka cluster, the shared resource of the Kafka cluster, we use 42, okay, whatever. But it's still hundreds of % more efficient to not do all the I/O and all the inefficient MapReduce that you have to do to process this much data. It doesn't make sense. AppNexus has been a streaming company from the very beginning. They did everything right. Everything is streamed around the world, and then when they went to actually process the data, they chose batch, which we sort of can't get rid of. And that's it. So thank you for listening. Thank you for your attention. And if you have any questions, I will love to answer them. Yes? Or just shout and I'll repeat it. What is the product that what? We don't sell anything unless you're in advertising. We make an ecosystem for people, buyers and sellers of advertising, to come together to make valuations, sort of like a stock exchange, but for ad space. Right? So we have ad impressions on the internet that are voluminous. Sorry if I wasn't clear earlier. Okay. Yes. Wait, in the back. He was first. No, that's a hard limit. Well, is that a hard limit? 120 milliseconds? It's per member, right? Yeah, it's a hard limit. We stop. We say, if you haven't gotten a response back in this sort of finite period of time, we're ignoring you, right? So it's the auction time is the auction time. That's it. It's our own SLA, yes. But in general, as you start to creep up towards 200 milliseconds, you actually can see the delay time on the page load, it's really just a user experience thing. I think a lot of those bidders who time out would appreciate having half a second. But there was one up front here. Yes?
Have you considered Apache Org instead of Arcade?
I have not. I'm sure the people that work on the batch side have looked at it. Yeah, is it awesome?
It is.
Okay. Then we will definitely take a look at it. Yes?
Your comments about Kafka. You wanted a hero. I think 0.9 will be your hero where you get to the zookeeper, which is the data bar as well. What's a good one to know?
Yes.
National buzz about the leader election. Big council, not the leader election. That one passed here already.
That's in trunk?
Should be in 082.
Okay. We run 082, and it still happens. So maybe they thought it was fixed? Or? Yeah.
0.9, no zookeeper will fix most of your shit.
Awesome. That would be the greatest day ever. But any idea what the release cycle looks like?
After lunch before Christmas.
Okay, good. Great. So, great. So I can ship something after lunch. I'm going to hold you to that. Other questions? Yes?
So you mentioned that you would do something other than C. I'm just curious about what you would actually do instead.
What would we do instead? I think on the less CPU bound, so we have two problems. We have one that is very I/O bound workload. We have all these requests for ads coming in and clicks and stuff. The machine, the impulse that faces the internet. That has less work to do. It's mostly waiting a lot of the time where it sends off requests to other bidders. They do the work, and then it gets something back and responds. I think we would write that in something else, a Java, I don't know. Do you guys have some other language? It's just that working in C is very difficult and very brittle, and it requires, as Paul had mentioned yesterday in his talk, it requires people who could go work on the kernel to write business logic, because our ecosystem is very, very complicated. Memory management or locks, or just you have to have a very, very accurate mental model of what's happening so that you don't take down the world by accident when you're just trying to make a new integration with some bidder, right? So it's fragile in that way, and we've built a lot of tools to make it less dangerous, but it's still not great for pace, for speed of development. Yes?
What was the technical decision to move away from Postgres instead of targeting Postgres?
I think at the time, and I wasn't there for this, so this is total conjecture, but I think at the time they just didn't know enough. In other words, I don't think it was a technical failing of Postgres. I think it was, hey, I'm frustrated with this, screw it, we're going to buy. And at the time, AppNexus was scaling so quickly, they needed to get a solution tomorrow, right? So they said, okay, we can go spend $500,000 and buy a Netezza, and that's going to work for tomorrow, and then we can solve this problem the right way, buy some time, effectively. So I think that's really what it was. People were out there tearing their hair out. Up front.
Yeah, is RatSoda open source?
No. Yes. The question was, is RatSoda open source, and will we consider open sourcing it? No, not yet. Yes. We're also, I'm working on open sourcing ANMessage for those of you who don't want to monkey with multiple formats and how to cross-communicate among different wire formats. It makes it pretty easy if you work in C or C++ or are okay writing FFI or something. We also have a version internally, which we will also try to open source, that does all of that stuff for ANMessage in Java and in Python. So we will try to release those all as a thing. I'm sorry? Packrat is not open source. That one, maybe, I don't know. It's not really not that interesting. I mean, like the way that we write apps, I think from a throughput and scalability standpoint, is more interesting than Packrat doesn't do much. It just gets data and unzips it and looks at every row and then combines it and then rezips it and sends it to somebody else. It's not really that complicated. There's not much to open source there, but the way we structure apps is actually interesting. So we have to talk about that because there's a lot of IP in that. So who knows? But I definitely have it on my lifetime goal list to open source a bunch of this stuff.
Would you build different connectors other than Kafka connectors to RatSoda?
So there is HTTP now. You can HTTP it. There's also a WebSocket. It's already built into the code base using libWebSockets, so you can communicate. It's a WebSocket server and client, so you can. Actually, we have. I don't have a demo up, but we've done demos before where we send impressions to RatSoda, and we have it real-time aggregate by geo. So it pulls off latitude and longitude from the impression, and it fuzzes it to a big circle, and then it counts all the impressions in that circle, and then it fires that information over WebSocket. So we can put a map up and have it go for all the impressions all over the world. It's pretty cool. Those kind of real-time visualizations are enabled by technology like this, but note that everything that RatSoda does is RAM. So if it goes down, you don't get something out of it, except for the joins, because the look back is so long, can't fit it in RAM. Yes?
You said you had 6 Vertica clusters.
Yes.
How big are they?
Oops. Hold on. No. Okay. There's 157 Vertica machines overall. The 06 Vertica cluster has 24 nodes. They're big. The reporting cluster is pretty big. That one has 48 nodes. So somewhere between 24 and 50, depending on what the cluster is being used for. We do get a lot of report requests, and generally there's an API request, run this report, and then we give them a token, and that report runs, and they keep checking, and they're polling, and eventually it's done, been generated in Vertica, and then we give them a link to pull the data. So that, like I said, there's 250,000 of those that are run every day on all various analytics on the platform. So we get a lot of Vertica traffic. Vertica is great. We're actually working on a project with Vertica to replace, we'll open source this too, to replace the Graphite backend storage with Vertica, because our metrics can no longer scale under Graphite in a reasonable way. We have 180 million metrics a minute that come off our platform, And we currently store these all in Graphite, in Whisper. And we don't have the greatest Graphite setup in that we scale these out by hand. So we move data when we bring up new servers to scale out the Graphite cluster. It wasn't the best setup. It hasn't been given much love. But it's also really expensive. We run Graphite on, I think, 80 bare metals, a lot of them with SSDs. It's huge. It's a huge operation. So we would like to replace that with just a Vertica cluster that can store all these metrics. So we are looking at rewriting Graphite storage. It'll be pin compatible so that you could just take the Graphite front end and plug it onto this thing, which will talk to Vertica. It's probably going to end up being a combination of Vertica for longer term batch load storage and maybe VoltDB for like a 15-hour cache of what's happening recently so that we have time to bulk load into Vertica. Same basic interface, because VoltDB is just a SQL in-memory Vertica-like thing. I'm talking about all kinds of stuff that doesn't even relate. Any other questions? No? Dope. Thank you, guys.